And so in a practical sense, you could say that the movement of a photon from one place to another, if you consider the movement of a photon from one place to another, from A to B, for example, this is already in quantum mechanics understood to be a sort of jump. If you try to start drawing the hypertime relationship between, you're mixing these 6 axes that each of them would have is their interference components through hypertime. And the problem you get into is we've only got 3 dimensions. And so when you look at 2, there's too many dimensions. Even if you use the concept that this wave might travel and curve back like we see electromagnetic waves doing. But the most important thing to remember is that this movement is a sort of illusion, that this movement itself happens because of the underlying magnetic translation. It's important to understand that this movement is a sort of illusion on the level of manifestation that results from the hypertime translation of the object through space. And so as we perceive this photon as traveling from A to B, how it is actually traveling from A to B is by its carrier that moves it not this way, but this way, in 6 different movements to arrive at point B, where it is perceived to be. And so it's the perception of this movement that has to be sorted out in astrotometry to understand the structure of the cosmos, to understand how matter and energy are composed. And this presents several huge conceptual issues that need to be worked through with respect to the nature of our perception of time and space. In quantum mechanics, the photon in some quantum mechanical schools is thought to be a complete unknown until it is actually observed. In quantum mechanics, the photon is thought to be a probability until it is actually observed. And some quantum mechanical schools will go as far as to say that it does not exist previously to being observed. Now, in astrotometry, I'm going to be proposing something called the grand illusion that relates to the nature of the light that comes from the distant stars. In astrotometry, if this is a distant star, and this is us on the Earth, we look at this, we see this light that travels from the distant star, and we assume that this is a straight trajectory. If you think about this as being 12 billion light years, it's highly unlikely that this ray, whatever it is, could travel directly to the Earth in a straight line. In a direct line from 12 billion light years away. This is an incredible distance. This type of distance is not something that we can even fathom as the scale of creature we are. But yet we believe, we model this as being a straight line from 12 billion light years away to the place on the Earth where it's observed. Well, if you consider the photon, if this is point A and this is point B, because of the nature of hypertime, because it happens in between time, that movement from A to B might be a single movement. In other words, that apparent photon that we believe, that we think is traveling as a wave, you know, all the way from 12 billion light years away to here on the Earth, that photon that quantum mechanics thinks maybe doesn't even exist until we observe it, might not even make that journey. This journey might be an illusion, might be some sort of grand illusion. So in other words, the nature of light as we perceive it as persistent, as traveling from one place to another consistently, may be a sort of illusion. And so the challenge that astrotometry will provide for scientists is to prove that this movement, that this path, is not actually a part of some higher dimensional form that appears because of an interference. For example, the reason that we believe that this happens is because if there's something in between, if there's something here, we see an eclipse. We see this star eclipsed. If the moon gets in the way, that star gets covered up. But what if the moon itself has something to do with the translation of the light itself through hypertime? In other words, what if the moon itself is interfering with this object's hypertime translation in such a way that creates the occlusion in a consistent way? In other words, it's mathematically consistent because of the underlying geometry. And so this is the challenge with astrotometry, is to understand the nature of this grand illusion. And so this is the thing that creates the different approaches to astrotometry that I've discussed in earlier videos. And so the approaches to understanding this are the more interesting, the interesting questions about the nature of the cosmos.